Bismillah ar-Rahman ar-Rahim. There are two sums in this video, a double sum and a single sum. Let's start with the double sum, which has these two parameters, alpha and beta. Beta is greater than 1 and alpha is less than beta. Let's split the sum into two sums. In the first sum, multiply the numerator and denominator by 1 over alpha to the m. So we get 1 here, and we get beta over alpha to the m downstairs. Note that both sums are similar. We have a double sum, m from 1 to infinity, n from 1 to infinity, 1 over m plus 1, n to the power m plus 1, then a number greater than 1 to the power m. Here we have beta over alpha, there we have beta. So we can just focus on this double sum and use eta here, where eta is greater than 1. Let's call this double sum omega of eta. If we obtain omega of eta, then our desired result is omega of beta over alpha minus omega of beta. Write 1 over m plus 1 as the integral x from 0 to 1 x to the power m. Note that all the terms are revalued and non-negative. By tonally, we can do our operations in any order of our choice. Do the summation first with respect to index m. We have summation m from 1 to infinity, x to the power m. Downstairs, we have n eta to the power m. X is between 0 and 1, small n is 1 or more, eta is greater than 1. This is a convergent geometric series. The sum is x over n eta divided by 1 minus x over n eta. The summand here is 1 over n eta minus x, and there is an x there. This can be written as eta over n eta minus x minus 1 over n. Here the terms are swapped, so we put a minus sign. In this summation, it changed n to n plus 1. Now we have a sum from 0 to infinity. The summand is 1 over n plus 1 minus eta over n plus 1 eta minus x. In this sum, divide the numerator and denominator by eta. This term becomes 1 over n plus 1 minus x over eta. Recall the di-gamma function, the logarithmic derivative of the gamma function. Epsilon of t is minus Euler's constant, small gamma, plus summation j from 0 to infinity, 1 over j plus 1 minus 1 over j plus t. The sum that we have here is small gamma plus epsilon of 1 minus x over eta. If we integrate, we get minus small gamma. The second integral is minus x from 0 to 1 d log gamma 1 minus x over eta. We need to multiply by minus eta, so I can replace this minus sign by eta like this. The integral is eta log gamma 1 minus 1 over eta minus eta log gamma of 1 minus 0, so that's gamma of 1, which is 1, and log 1 is 0. What we have is eta log gamma of 1 minus 1 over eta. This is omega of eta. The double sum that we have is this difference here. Small gamma disappears, and we get that the double sum is beta over alpha log gamma 1 minus alpha over beta minus beta log gamma 1 minus 1 over beta. Let's now move to the second sum. We have summation m from 1 to infinity, 3m choose m, 1 over 8 to the power m. To obtain this summation, one way is to investigate the generating function of 3m choose m. To obtain this, we may need the hypergeometric function or other special functions. The result that we get is, after obtaining the generating function, we can just put z equal to 1 over 8. I will not employ any special function. I will use a probabilistic interpretation of this sum, which emerges in the context of random walks. Suppose that we have a sequence of two valued random variables, d1, d2, d3, and so on. The random variables are IID, independent and identically distributed. Each of these random variables is either equal to 2 with probability 1/2 or minus 1 with probability 1/2. Define the random process xn, where n is a non-negative integer, x0 is 0. When n is a positive integer, xn is summation k from 1 to n dk. So x1 is d1, x2 is d1 plus d2, x3 is d1 plus d2 plus d3, and so forth. This random process is called a random walk. Note that it moves on the lattice of integers. Starting at any integer, the process either goes to the right by 2 steps. If we are here at v, then we go to v plus 2 with probability 1/2, or we go to the integer v minus 1 with probability 1/2. Consider some small n. Suppose that the random walk makes n1 steps to the right. This means that in this summation here, there are n1 terms, each one of them is equal to plus 2. Suppose that the random walk makes n2 steps to the left. In this summation here, we have n2 terms that are equal to minus 1. n1 plus n2 is equal to n. What is the value of xn? xn is equal to plus 2 times n1 plus minus 1 times n2. xn is equal to 2n1 minus n2. If xn is equal to 0, which means that the process is back at the origin, then 2n1 is equal to n2. N is equal to n1 plus n2, which is 2n1, that's 3n1. In this random walk, we are possibly back at the origin at values of n that are multiples of 3. The probability of the event that xn is equal to 0 is possibly non-zero when n is equal to 3 times the positive integer m. What is this probability exactly? That this summation here is equal to 0 given this initialization. For xn to be equal to 0, in 3m steps, there must be 2m terms in this sum equal to minus 1. The remaining m terms are equal to 2. The probability of a particular sequence of 3m steps is 1/2 to the power 3m. Then we need to multiply by 3m choose m to account for the fact that in this sum with 3m terms, we need m terms to be equal to 2, or alternatively, we need 2m terms to be equal to minus 1. The probability that x of 3m is equal to 0, which means that the random walk is back at 0 after 3m steps, is 3m choose m, which is equal to 3m choose 2m, multiplied by 1/8 to the power m. This is the summand that we have. What does it mean that we sum those terms over positive integer m? After initialization, suppose that we are tracking the number of visits to the origin to 0. Denote the number of visits by v. V is equal to summation n from 1 to infinity, indicator xn is equal to 0. So this is 1 if xn is equal to 0, 0 otherwise. We are sure that if small n is not a multiple of 3, it is impossible for the process to be back at the origin. We can write v as summation m from 1 to infinity, indicator x of 3m equal to 0. What is the expected value of v? On average, how many visits to the origin occur? This is a non-negative quantity. By Tonelli, we can interchange the order of expectation and infinite sum. What is the expectation of indicator x3m equal to 0? This is a Bernoulli random variable. The expectation is 0 times the probability that this indicator is 0 plus 1 times the probability that this indicator is equal to 1. This expectation is equal to the probability that x of 3m is equal to 0. And this probability is 3m choose 2m or 3m choose m divided by 8 to the power m. The sum that we are interested in has this probabilistic interpretation. We have a random walk carried out with these steps. We start at the origin. We ask the question, on average, how many visits to the origin take place? The expected value of v is the result we are hunting for. Define f00 to be the probability of ever re-entering the origin if the random walk starts at the origin. What is the probability that v is greater than or equal to 1? The random walk makes 1 or more visits to the origin if it sooner or later goes back to 0. This happens with probability f00 by definition. What is the probability that v is greater than or equal to 2? Which means that the origin is visited at least twice. We start at the origin. We need to go to the origin for the first time, and this will happen with probability f00. We are now back at the origin. The random walk starts anew. What is the probability that 0 is visited again? This happens also with probability f00. I wrote that the probability of the event v greater than or equal to 2 is f00 squared. The reason for this, without going into excessive detail, is that our random walk is a Markov process. Once the origin is visited, the future and the past of the process are conditionally independent. The principle justifying that we write the probability in this way is called the strong Markov property. The idea is also intuitive. From the structure of the random walk, it is clear that if some integer is visited at some time instant n, given that the future of the random walk doesn't care at all about how this integer has been reached. What is the probability that there are 3 visits or more? The random walk starts at 0. We need to go to 0, and this will occur by definition with the probability f00. Once we reach 0 again, the problem is restarted. What is the probability that 0 is visited sooner or later? That's f00. Then to have 3 or more visits, we need to make the 3rd visit, and this will happen with probability f00. The probability that v is greater than or equal to 3 is f00 to the power 3. Our result of interest is the expected value of v. This is summation n from 1 to infinity, and the probability that v is equal to n. Let's write this n here as summation k from 1 to n of 1. The summand is real valued and non-negative, so by Tonelli we can interchange the order of summation. Here we have an outer sum n from 1 to infinity, an inner sum k is from 1 to n. Equivalently, we can have an outer sum k from 1 to infinity, and n is from k to infinity. This summation here is the probability that v is greater than or equal to k. From the argument above, this probability is f00 to the power k. As a geometric series, this sum is f00 divided by 1 minus f00. Of course, there is a question here. Can f00 be equal to 1? If this is the case, then this geometric series is divergent. There is another story here. In principle, in a discrete time Markov chain or a random walk, f00 may be equal to 1. However, in our problem, the states, the integers that are visited during the random walk, are transient. Transient means that if we initialize the random walk at any integer, then there is a strictly positive probability that this integer is never visited again. f00 must be strictly less than 1. There is a positive probability, 1 minus f00, that starting at the origin, the random walk will never ever come back to the origin. We can take this for granted here. If we are able to obtain f00, and we should find that it is strictly less than 1, we are done. We are able to compute this expected value, which is exactly the sum of interest. Define eta n as the probability to ever visit the origin if the random walk starts at n. We take eta 0 to be equal to 1 because our random walk starts at 0. We will obtain f00 by obtaining eta n for n that is non-zero. The key idea here is to write down a difference equation for eta n. If the random walk starts at the integer n, there are only two possibilities. The random walk either moves to n plus 2 with probability 1/2 or to n minus 1 with probability 1/2. So for n that is not equal to 0, eta n is 1/2 eta n minus 1 plus 1/2 eta n plus 2. This recursive or difference equation is the key to obtaining our solution. The difference equation here is solved in a standard way. The characteristic equation is 1/2 lambda cubed plus 1/2 lambda to the 0 equal to lambda. This can be written as lambda cubed plus 1 equal to 2 lambda. That's a cubic polynomial. 1 is a solution to the equation lambda cubed minus 2 lambda plus 1 equal to 0. Knowing this, we can factor lambda cubed minus 2 lambda plus 1 as lambda minus 1 and lambda squared plus lambda minus 1. Lambda squared plus lambda minus 1 is 0 if lambda is square root 5 minus 1 over 2 or minus 1 minus square root 5 over 2. Our difference equation has the solution. Eta n is a constant times 1 to the power n plus another constant times this guy to the power n plus a third constant times this number here to the power n. It is important to keep in mind that this number here is in the open interval from 0 to 1. This number here has a magnitude that is strictly greater than 1. Let's focus first on non-negative n. Eta 0 is equal to 1 because we start the random walk at 0. Our first equation is that C1 plus C2 plus C3 must be equal to 1. Note that eta n is a probability. This term here is problematic because the magnitude of this number is greater than 1. If C3 is not equal to 0, then the magnitude of this term grows without bound. Thus, C3 must be equal to 0, and C2 is equal to 1 minus C1. This is the situation right now. How can we obtain C1? If we start the random walk at a very, very large positive integer, then the probability of ever visiting the origin diminishes. We can say that as a small n tends to infinity, the probability of ever visiting the origin tends to 0. Since this number is strictly less than 1, then the limit as n tends to infinity of eta n is equal to C1, then C1 is equal to 0. This is eta n when n is non-negative. If n is non-positive, we still have the same general solution to the difference equation, but now we have three constants, C1 bar, C2 bar, and C3 bar. Eta 0 is 0. The sum of the three constants is equal to 1. The magnitude of this number is strictly less than 1. This term here is equal to 1 over minus 1 plus square root 5 over 2 power absolute n. This is greater than 1. The magnitude of this part tends to infinity. As n tends to minus infinity, we need C2 bar to be equal to 0. Consequently, C1 bar plus C3 bar is equal to 1. How can we obtain C1 bar? Recall our recursion. When n is not equal to 0, we have that eta n is equal to 1/2 eta n minus 1 plus 1/2 eta n plus 2. We can employ this with n equal to minus 1. That is, we have eta of minus 1 is equal to 1/2 eta of minus 2 plus 1/2 of eta of 1. Eta of 1 is obtained from this expression after setting small n equal to 1. eta of -1 and eta of -2 depend on the constant C1 bar. We have one equation in one unknown. When we solve, we get that C1 bar is 3 square root 5 minus 5 all divided by 2. This is the expression for eta n when n is non-positive. This is C1 bar, and this is 1 minus C1 bar. What is F00? By definition, F00 is the probability that at some positive time instant n, the random walk is back at the origin. What is eta n? We start at integer n, and we ask what is the probability that at some non-negative n, the random walk is at the origin. If we start at the origin, then we either go to 2 with probability 1/2 or to -1 with probability 1/2. This means that F00 is 1/2 eta 2 plus 1/2 eta -1. We use this expression with n equal to 2 and that expression with n equal to -1 to obtain F00 as 9 minus 3 square root 5 over 4. Starting at the origin, the expected number of visits to the origin is F00 over 1 minus F00, and this is the summation of interest. This summation is this number divided by 1 minus this number. Doing the calculation, this is 3 over the square root of 5.